purpose of this lesson is to study plane electromagnetic waves in lossy media. Lossy media means that we have some absorption of the fields, and therefore we expect a dissipation term. We expect a change of the value of the amplitude of the wave as a result of dissipation. So, in lossy media, what do you have to characterize lossy media? We can have a complex permeability in the form of a magnetic loss tangent, tangent delta mu. We can have a complex permittivity in the form of an electric loss tangent, tangent delta epsilon. And we can also have conductivity in the material in the form of Ohm's law. So we can have a non-zero sigma in the material. As you see, we can summarize Maxwell's equation with the specific shape of the field that we already introduced when we studied waves in lossless materials, with adding complex numbers, complex parameters in mu, epsilon, and the introduction of sigma if there is a non-zero conductivity. So that what happens to the wave equation? Now the wave equation that is formally the same as before, but has now a complex coefficient in the term that multiplies, for instance, Ex. We can call again this complex coefficient minus k squared, as we did for the lossless case, but now since k squared is complex, k is now complex. And we can write this wave number, new wave number, complex wave number, in the form of real part minus j imaginary part. The reason why you use this minus will be clear in a while. After substituting, as you see, we obtain k as the square root of the complex number minus j omega mu that multiplies sigma plus j omega epsilon, in which we can have non-zero sigma, we can have complex permeability, and we can have complex permittivity. So that our wave that propagates along the positive z direction will have a positive beta, propagation constant, but also a positive alpha that represents an attenuation constant. And this minus sign ensures that the wave attenuates along the positive z direction. So that we can formally write for the electric field in the material an expression that is exactly equal to the previous one, but the previous one for the lossless case. But now k is, as you see, complex. So that also eta, which represents the relationship between electric field and magnetic field, the wave impedance, is complex, because we can have complex value for mu, complex value for epsilon, and non-zero conductivity. Once we split this k, which is complex, shown here, into their beta minus j alpha components, we obtain an expression for the wave function in this form, in which we have still a term that represents propagation along the positive z direction, and the term that represents attenuation in the positive z direction. Also, the relationship between Ex and Hy is now complex in the form of a complex impedance. Now, we can specialize to two cases. The case of real conductors, in which we have non-zero conductivity, but real permittivity and real permeability, even if this can be also complex in conductors, and the case of dielectrics, in which we have a non-zero loss tangent for the material. The loss tangent is, let's say, a parameter that comes with the description of the dielectrics. Also, when we buy the material to realize a circuit PCB, there is, among the other parameters, also the value of the loss tangent, so that dielectrics are typically characterized by a value, a non-zero value of loss tangent. We study first the case of dielectrics, in particular the specific case of good dielectrics, in which the loss tangent is much less than 1. This represents the most common case for dielectric materials. In that case, we can apply some simplification to our expression of the complex wave number k, which can be written by rearranging the terms as alpha plus j beta. And in particular, when the loss tangent is much less than 1, we can simplify this expression to this term, beta over 2 the loss tangent plus j beta. So this is alpha, which is beta over 2 times the loss tangent, and this is beta. And since the loss tangent is much less than 1, also alpha is much less than beta. At the same time, the good dielectric case allows us to use for the wave impedance a real number. So we can neglect the presence of the loss tangent in the expression for epsilon in the eta parameter in the wave impedance. Materials have, in general, very different loss tangent. According to this classification, the table that you see here represents some materials. Most of these can be considered good dielectrics, but some of these cannot be considered good dielectrics, such as the distilled water, for instance. When we are willing to use a specific material as a dielectric material for the use of a circuit, for instance, we should take care that this material is good dielectric, so its loss tangent is very small. Another important case is that of good conductors, in which sigma is much greater than omega epsilon. This is another special case that we treat separately. As you see, this condition involves also frequencies, so that you cannot expect to hold for all frequencies. But let's have a closer look at this condition. In particular, we're interested in some exemplary cases in which we have several good conductors that are typically used in circuits such as aluminum, gold, copper, silver, but also some more common materials such as seawater. As you see, in very good conductors, conductivity is of the order of 10 to the power of 7. So when are we in this condition? And another question could be, what happens with seawater that has a much lower value of conductivity? Up to what frequency does this condition hold? So let's consider a value for this condition to hold that corresponds, for instance, to sigma being equal to 100 omega epsilon. So that this means that if omega increases over that value, we are no longer allowed to say that this is a good conductor. It is just an indicative value. If we substitute the value of conductivity of seawater, and you write also epsilon r of seawater and impose this condition, we observe that this condition, sigma equals 100 omega epsilon for seawater, is met at a frequency of 9 megahertz. So that for frequencies less than 9 megahertz, according to this condition, we are allowed to say that water is a good conductor. What happens for copper? The same condition is met at a frequency that is much larger, of the order of 10 to the power of 4 terahertz, an extremely high frequencies. And we cannot surely expect that the conductivity of copper has the same value from DC up to such high frequencies. So let's say that anyway, copper is a very good conductor up to the frequencies of interest in the telecommunication world, let's say up to hundreds of gigahertz. This is the typical frequency range in which we usually work. What happens in good conductors? We can, as you see, simplify the expression of alpha plus j beta by neglecting omega epsilon with respect to sigma, so that to obtain this expression for alpha plus j beta that tells us that alpha and beta have the same value, which is, as you see, omega mu sigma over 2 under the square root sign. So this term represents a function that, as a function of z, you see here the magnitude, the attenuation, exponential minus, in this case we used x as a variable, but minus x over delta minus alpha x, and it's the attenuation, and we also have the oscillation represented by beta, this one and this one. Now the inverse of alpha is called skin depth, is the depth of penetration. What are we meaning is that, looking at this picture, the area of this exponential function from 0 to infinity equals 1 times this length, delta, and this length is 1 over alpha. This means that we can think of the fields in a very good conductor as being confined to a very narrow region of thickness delta. Usually this skin depth, this thickness, is very, very small. If we do the computation for some common conductors, we observe, for instance, that in copper, At 1 gigahertz, in which the conductivity is 5.8 10 to the 7 Siemens per meter, as you see here with the skin depth in microns, and we are of the order of 2 microns. So it is very, very thin, the region in which the fields are non-zero. Then, after delta, we can consider the fields as being zero. So if we have an arbitrarily shaped body that is made of a good conductor, and externally we have some fields, the field penetrates inside the material for a small thickness delta. So in summary, the wave, as it propagates inside a lossy material, suffers from an attenuation, and therefore its amplitude decreases as a result of absorption, partial absorption of the wave. The general shape in terms of beta and alpha can be recovered by taking the square root of the material parameters shown here. There are special cases that we have discussed, and particularly good dielectrics and good conductors.